Welcome. Today, we're diving into the work of Dr. S.K. Singh, focusing on forced degradation studies and stability indicating methods. These are essential tools in understanding how substances change over time and under stress. Let's explore how these techniques help ensure safety and effectiveness in pharmaceuticals and beyond. Let's start by looking at forced degradation studies, sometimes called stress testing. This process means deliberately exposing a drug or its components to harsh conditions. Why? To speed up how it breaks down and to uncover the ways it degrades. Our goals here are clear: to understand those breakdown mechanisms, map out the degradation pathways, and develop stability-indicating methods that can detect changes accurately. These studies also prove method specificity, help profile impurities, and support formulation development. They're a crucial part of both analytical method development and meeting regulatory expectations. Let's take a look at the regulatory framework guiding our work. We rely on a set of international guidelines from the ICH, covering everything from stability and photostability testing to impurities and analytical method development. Alongside these, pharmacopoeial references like the USB and European Pharmacopoeia provide detailed standards. The main goal here is clear: to demonstrate that our analytical methods can accurately measure the active ingredient, even when degradation products or impurities are present. This ensures reliability and safety throughout. Let's talk about stability indicating methods, or SIMs. These are special analytical procedures designed to measure the active ingredient in a product, and nothing else. They're validated to ensure they're not fooled by degradation products, impurities, excipients, preservatives, or even contaminants from packaging. What makes a good SIM? It needs to be specific, accurate, precise, robust, and sensitive. Plus, it must confirm peak purity, so we know exactly what we're measuring every time. Let's talk about how materials break down over time, the common ways they degrade. First, there's photolysis, where light, especially UV and visible light, causes chemical changes. Then, humidity plays a big role. Moisture gets absorbed, leading to hydrolysis, which can happen in acidic or basic conditions, breaking molecules apart. Oxidation is another culprit, with oxygen or peroxides attacking the material. And of course, heat speeds up all these processes. Take aspirin, for example. It hydrolyzes into salicylic acid and acetic acid when exposed to moisture. When we talk about forced degradation, the goal is clear: to create meaningful breakdown of the analyte, but without completely destroying it. We want to stress the sample just enough to see how it behaves under tough conditions. These conditions include acid and base hydrolysis, using mild concentrations of hydrochloric or sodium hydroxide. Oxidation is another key stress, often with hydrogen peroxide. Then there's heat, humidity, and exposure to light, all typical ways to challenge the stability of a compound. This approach helps us understand its limits. Now, let's look at the analytical tools we use to understand drug stability. We rely on techniques like HPLC, UPLC, and LC-MS for precise chemical analysis. GCMS and NMR help us identify degradation products. Our experimental design covers testing the drug substance alone, under various stress conditions, and the finished drug product. We also assess how excipients interact. Key evaluation parameters include assay loss, impurity generation, peak purity, and mass balance, all critical to ensuring drug quality. Let's take a closer look at an acid degradation study, a key example that shows how substances break down under acidic conditions. This kind of study helps us understand stability and lifespan, especially for sensitive materials. By simulating harsh environments, we can predict how products will perform over time and identify any weak points before they cause issues. It's a crucial step in ensuring safety and effectiveness. Now, let's look at an example of an oxidative degradation study. This type of study helps us understand how a material or compound breaks down when exposed to oxygen over time. It's crucial for predicting shelf life, stability, and safety. By examining the changes that occur during oxidation, we can identify potential weaknesses and improve formulations. This example will guide us through the process and highlight key observations. Now, let's talk about mass balance calculation. This is all about tracking the flow of materials in and out of a system to make sure everything adds up. We measure inputs, outputs, and any changes within the system. It's a fundamental step. It helps us understand efficiency, detect losses, and optimize processes. Without a solid mass balance, we're flying blind. So mastering this calculation is key to making informed decisions and improving performance. Now, let's turn to peak purity assessment. This is where we evaluate the clarity and quality of the signal at its highest point. It's a crucial step, because a pure peak means our data is reliable and free from interference. By focusing here, we ensure that what we measure truly represents the substance or signal we're analyzing. No noise, no distortion, just the cleanest possible result. When we talk about method validation requirements, we're focusing on the essential steps that ensure a process or test is reliable and accurate. This means confirming that the method consistently produces results we can trust. Validation isn't just a checkbox, it's the foundation for quality and confidence in our work. Without it, we risk errors and inconsistencies that can undermine everything we're trying to achieve. So, understanding these requirements is key to building methods that stand up to scrutiny every time. In this case study on paracetamol tablets, we developed a stability indicating method that successfully separated the API peak from 5 degradation products. Each peak had a resolution greater than 2.5, ensuring clear distinction. When we stressed the samples, the highest degradation occurred under oxidative conditions, with 15.8% breakdown. Acid and base conditions also caused notable degradation, while thermal and photolytic effects were less significant. These results help us understand how the drug behaves under different stresses and guide its stability assessment. When regulators review stability studies, they often flag a few common issues. Stress testing might be inadequate, producing too little degradation to be meaningful. Sometimes, peak purity data is missing, so there's no proof the method is specific. Poor mass balance means degradation products aren't fully accounted for. Co-eluting peaks can hide the active ingredient among degradants, and if the method isn't properly validated as stability indicating, that raises red flags. These gaps can lead to deficiency letters and slow down approvals. We need to address each one carefully. In pharmaceutical development, forced degradation studies and stability indicating methods are essential. They help us ensure that drugs stay safe and effective throughout their shelf life. Meeting global regulations means we need scientifically justified stress conditions, thorough degradation analysis, and full validation that complies with ICH guidelines. These studies identify how a drug breaks down, support impurity profiling, and help us develop reliable analytical methods. Meanwhile, stability indicating methods must prove they're specific, accurate, precise, and capable of confirming purity and mass balance. This is how we achieve regulatory success. Thank you all for being part of this conversation. If you need any more support or have questions, please don't hesitate to reach out. We're here to help. Thanks again for your time and attention. It's been a pleasure sharing this with you.